Okay, welcome back. Last time we got into some discussion regarding the mutual information and the conditional mutual information, and why we try to compare these two quantities, and this lead to some discussion on independence and conditional independence. And basically, to just summarize a little bit, for independence, we gave an example like this, like xy given z. Xy are independent and z are actually dependent on x and y. And for conditional independence, we have a example is kind of like opposite, that we have z and xy is kind of depend on z and do not depend on each other directly. And if it's kind of interesting that like they're kind of like opposite to each other in the sense that in the first example, xy are independent at the beginning, but if we observe z, then xy will no longer be independent. So that is like pxy is equal to pxpy, but we don't have pxy given z naught, let's say, is equal to px given z naught and py given z naught. So this is like after you observe a z to be z naught, we no longer able to decompose this x and y into factors. I mean pxy given z naught into factors that each factor only contain x and y, x or y. And in this second case here, we don't have pxy to be independent, so x and y are not actually independent. But on the other hand, if we observe z, so I should put a cross here. If we observe a z, then basically we will have pxy given some z naught. Let's say if the observation is z naught, we can decompose the probability into px given z naught and py given z naught. Okay, let's try to give each of these one example here. How about start with this one first? Let's say I have x is like binary random variable 0 and 1, and y are binary random variable 0 and 1 also. Then let's say z is just a bitwise addition of like x and y, and let's say x and y are independent. So, and let's say these are all equally likely probable also. So probability of 0 and 1 for each of these cases are 1/2. Then I have, let's look at what is ixy of course is equal to 0 because x and y are independent. So now ixy given z is basically equal to hx given z minus hx given y z here. Now given y and z, basically x is deterministic because x is equal to y, z equal to x plus y will imply that x is equal to y plus z. Basically, I just add y on both sides, left hand side and right hand side. So therefore, this will go to 0 because x is deterministic given y and z, and hx given z is basically equal to hx given z equal to 0 plus p z equal to 0 plus hx given z equal to 1, p z equal to 1, and so on. Now if I look at the probability distribution, let's say when z equal to 0, x and y can take 0 and 1. So if z, I know that has to be 0, then x and y can either be both zeros or both 1. So therefore, like the probability distribution will be like 1/2 here, 1/2 here, and 0 here. So therefore, like hx given z equal to 0. Okay, in this case, probability x equal to 0 and 1 is still 1/2. Basically, probability x equal to 0 will be this column, right? And the probability is just 1/2. And probability x equal to 1 is this column, is 1/2. So therefore, hx given z equal to 0 is basically is h 1/2. That's 1 bit. And similarly, for this case, this is 1 bit also. Therefore, I will just have 1 multiplied by 1/2 plus 1 multiplied by 1/2 by minus 0 here. That's basically just 1 bit. So now in this case, I have like basically ixy given z is bigger than or equal to ixy. So because I have x and y are independent, but x and y are not conditionally independent given z. So let's try to give one example for this case here. Let's say I have z is again a binary random variable with outcome 0 and 1, and probability of both again is uniform. Both 0 and 1 have probability 1/2. And let's say x is equal to, let's write like this. Okay, x is again binary, and let's say we have a kind of pseudo channel that z, or like I can just think of like x is equal to z plus u, and u, let's say, is binary also 0 and 1, and but you have probability of 1, let's say, is 0.1, and probability of 0 is 0.9, let's say. And similarly, let's say y is equal to z plus v, and again, the v has the same distribution as u, basically taking 0 with probability 0.9 and 1 with probability 0.1. Now, we assume that u, v are basically independent of z here. So u independent of z, v independent of z, and u independent of v, and so on. So now in this case, we can see that basically given z, so first of all, like we can see that x and y cannot be independent. We have kind of like a channel from x and y. Basically, x and z is related to, or like I can just simply write like this, I guess. X plus y is equal to u plus v, right? And so therefore I can write x, because I just like this add this and this add this, and z get cancelled because these are all piecewise addition. So I can write like y. Okay, I can add x here also. It's equal to u plus v plus z. So u plus v, I can think of another variable. Let's call it w. And what's the probability of w to be 0? So probability of w to be 0 will be either uv is 0 or uv is 1. That's basically 0.9 times 0.9 plus 0.1 times 0.1. That's 0.82. And the probability that, okay, or like, let me put it this way, 0 and 1. The probability to be 0 is 0.82, and therefore probability of 1 is basically 0.18. So we consider x and y is actually quite a bit, sorry, this is not c here, this is x. X and y are quite a bit correlated. It's like, basically is we have pretty high chance that x and y will be equal, about like 0.82 probability that like x and y will be equal, and 0.18 probability that will not be equal. So apparently, therefore, x and y are not independent. Not independent. But if we observe z, for example, if we know that z is equal to 0, then what happens is like x will be just equal to u, and y is just equal to v. And we already say that u and v are independent, therefore x and y are independent. And for the other case, it's true also. If z equal to 1, then x is just equal to 1 plus u, and v is equal to, y is equal to 1 plus v. Again, u, v are independent, this x and y will be independent. Because basically one is just flipping the two independent variables. And if they are independent at the beginning, this variable, after flipping them, they are still independent to each other. Of course, I can verify that. Let's verify that with by computing the mutual information and the conditional mutual information. So let's see what is IXY. IXY is basically, in this case, is h x minus, let's say h. I have hy already here. Let's say do hy minus hy given x. Let's say, and hy given x we see is equal to w here, is equal to hy minus hw. And I know that by the setup here, y, the probability of y is probability of y equal to 0 is basically 1/2, because okay, probability of y equal to 0, let's just write it, this will be equal to probability z equal to 0 multiplied by probability v equal to 0 plus probability z equal to 1 plus probability z equal to 1, and probability z equal to 0 is 1/2, so it's 1/2 times v equal to 0 is basically we say it's 0.9 plus 1/2 plus 0.1, and this would be just equal to 1/2. So therefore, like, probability y equal to 0 is just 1/2, and y equal to 1 is also 1/2. Therefore, hy is just equal to 1, and hw, as we show that w is have the distribution, probability of 0 equal to 0.82, and probability of 1 is equal to 0.18. Therefore, it's equal to 1 minus h.18. So this is apparently not 0, it's bigger than 0. And if you look at ixy given z, that would be equal to hy given z minus hy given x and z, let's say. And what we have is y is basically equal to at the beginning here, y is equal to z plus v, and v is independent of z. So actually, basically, we can write at the beginning that we can know that given z, just by the Markov chain, actually, given z, x is independent, and therefore, like, we have hy given xz is equal to hy given z. So therefore, this will be equal to 0. These two terms will just cancel. So okay, that's what we have here now. So we have an example. In this case, is ix y is bigger than ix y given c. So we have example for both cases.